Hi everyone, Mr. Rowe here. I thought I'd start off this new unit with a video lesson because I was going through it, I was filling out the note, and there were some pretty scary looking formulas, so I didn't want anyone to see that and get worried when they're really nothing to be scared about at all. So I thought I'd just work through it with you. Again, this is kind of a hybrid. I've got a little bit of the note filled out already. Some of it I'll work through with you and it's blank, but let's get started. So this new unit is on statistics of two variables. So the last unit was statistic on one variable, whatever the variable was, marks, height, weight, and we did mean, median, mode, standard deviation, all those one variable statistic calculations. But now we're going to be looking at two variables. So for example, does smoking cause lung cancer? So the two variables are smoking and lung cancer. Is job performance related to marks in high school? Do pollution levels affect the ozone layer? Does your height affect the IQ? So it's all about trying to show that one variable is causing the other variable to change. Okay, so this might sound familiar to you, because if you think back, if you go in your time machine 4 years ago to grade 9, you did statistics of two variables. So we're going to take it up a notch now that we're in grade 12, but you should be familiar with some of this scatter plots and linear correlation stuff from grade 9. We're just going to build on it. So often the answers to these questions, they're not clear cut, so we have to sometimes make some inferences. What we're going to do is we're going to have methods for detecting these relationships between the variables and then making some mathematical models. So recall from grade 9, a scatter plot shows a graphical relationship between the independent variable x and the dependent variable y. So what we want to determine, as I mentioned above, is does y depend on x? Is the change in x causing the change in y? And you would have remembered from grade 9 if you're in my class, or I used to do this height versus reach scatter plot. So does your height have an impact on your reach? And then I took everyone's height and reach, we put on a scatter plot, and then we classified the correlation. So just as some recalls, the line of best fit is a straight line that passes as close to all the points as possible on the scatter plot. The stronger the correlation, the more closely the data points cluster along the line of best fit. A perfect positive correlation exists when y is increasing at a constant rate. So that means the line of best fit will go through each point in a positive way, so going up. Whereas the perfect negative linear correlation is the reverse. Y will be decreasing at the constant rate. So the line of best fit will go through each x value going downwards. So we're just going to have a look at a few examples here. On your notes, I don't think you have these scatter plots drawn in. So you can pause the video and fill in these scatter plots. And all we're doing is like you did in grade 9. I could have asked you this in grade 9 and said, classify the relationship between the two variables, if one exists. So what we want to do is we want to include a strength. We could have weak, moderate, or strong, and also a direction. And of course, the correlation doesn't have to be linear, but if it is, we should probably include that it's linear as well. So starting with this, here I'll get out a red line here. If we were to draw a line of best fit, clearly there's a relationship here between the independent variable and the dependent variable. As x increases, y increases, and notice how tightly clustered these points are around the line of best fit. So I classified that one as a very strong positive. So it's strong because they're tightly clustered around the line of best fit. It's positive because it's going up, and it's linear correlation because it resembles a line. A line of best fit is appropriate to be used. The next one we have here, if you notice, if I were to go to draw a line of best fit, all the points go on the line of best fit. So that means that this is a perfect negative linear correlation. So as x increases by a specific amount, y is decreasing by a constant amount. Now, what do you make of this? Could we fit a line of best fit on this? Well, no. So there doesn't have to be a correlation. You could plot the relationship between two variables, like height and IQ, for example. Could have had your height here and your IQ here, and you'd have a lot of tall people with high IQs and low IQs, a lot of shorter people with high IQs and low IQs, and people all in the middle. There would be no correlation. So we just say there's no correlation between these two variables. Then we have this one here. So, you know, the points aren't that clustered, but if you could still draw a line of best fit. It probably looks something like that. So it's definitely positive, but it doesn't feel very strong to me. So you could use a word like moderate, and because it's going up, we're going to say moderate positive linear correlation. So we kind of have a similar situation happening here, except that the points seem a little more spread out. So again, this is a little subjective, but I would consider this a weak positive linear correlation. And then lastly, you know, it's not quite as strong as this one, but I wouldn't say this is moderate either, so I called this a strong negative linear correlation. Again, it is open to a little bit of interpretation. As long as you can justify it, then you should be okay. So that's grade 9. So scatter plots will only give you a rough indication of the correlation. What we're going to be able to do is use a formula that's going to tell us the exact correlation. So first, before we get into that, we'll talk about the covariance. The covariance of two variables in a sample. So to develop a measure of correlation, you first define what's called the covariance. And again, it's this kind of like scary formula here. So what you have here is, we've seen these symbols before. This is the Greek letter sigma. It means the sum of. So what do they want you to add up? They want you to take each data point, subtract the mean, so basically the deviation of x. And because you have two variables, you also have a deviation of the y variable. So they want you to take the deviation of that x variable and the deviation of the y variable and multiply it together. And then you're going to do that for every pair of points, add them up, and then it looks like you're going to divide by n minus 1. So that'll give you what's called the covariance. Don't worry about this. What we're interested in is this, what's called a correlation coefficient. It's an R value. So what it is, by definition, it's the covariance divided by the product of the standard deviations of x and y. So is this the formula we're going to use? Not exactly. What this R value is going to eventually tell us, though, is how closely the data points cluster around the line of best fit. So what do I mean by that? When we use this formula or version of this formula, it's going to spit out a number, and that number will have context and meaning for us. It will spit out a number between -1 and +1. So if it's a negative value, that would imply a negative correlation. If it's a positive value, it would be a positive correlation. And the closer the value is to 1, the stronger the correlation. So for example, if you got a R value of 0.9, that would be very close to 1 and positive, so it would be a strong positive. Now if you got, -0.2, that would imply a negative correlation, and it's less than a third, so it would be considered weak. So there's two kind of versions of this formula. The first one we've already seen. It's where you take the standard deviation, or the standard deviation of x, multiply it by the standard deviation of y, and then you use the covariance of x and y. So that's a lot of calculations. Like just calculating the standard deviation of a variable is a lot of work. So you'd have to do that for both of the variables, and then also go back and use this formula for the numerator. Luckily for us, somebody has made the process a little bit easier. You might not think so by looking at this, but this formula is actually not terrible. So this is the scary formula I saw as I was filling out this note, and I said, alright, I think I should do a video lesson here. I don't want anyone to see that and shut their book. So this is the formula for the R value, but it's really not that scary. Basically what you do is you take the number of elements, and then you're going to multiply it by the sum of, you're going to take each x multiplied by y, add it up. Then you're going to subtract the sum of x and the sum of y multiplied by each other, divided by the square root. And look, there is some symmetry to this, right? Like if you were writing an assessment in class, I would actually have you memorize this formula. But that won't be the case when you're doing your assessment. You'll have this in front of you, so it shouldn't be a problem. So you're just going to go n times the sum of the x value squared minus the sum of x squared. So there is a difference here. Basically, for this here, you're taking all the x values, squaring them, then adding those up. Whereas this is you add up all the x values, then square them. You do the exact same thing for y. You multiply those values together, you take the square root, and you put in all your calculations, and you should absolutely get a value between -1 and 1. And we're going to do an example of this on the next page. So this is the formula we're going to use. And here's our example. So this farmer here wants to determine if there's a correlation between the average temperature during growing season and the size of his wheat crop. So, just thinking about it before we even get started here, it would make sense that, the higher temperature should probably produce more crop. So we're not going to rely on speculation and guessing. We're going to prove this mathematically. So the first thing I'm going to do is create a scatter plot. So mean temperature is 4. I don't know what happened here. My graph's cut off. Hopefully yours isn't. So I'm going to assume these go up by 1. 1, 2, 3, 4. And 1.6 would be like right here. Maybe we'll make that a little thicker. Okay, 8, 5, 6, 7, 8, and 2.4 would be about here. 10 and 2, 9 and 2.6, 11 and 2.1, and then 6 and 2.2. 1, 2, 3, 4, 5, 6, and 2.2. Okay, so we don't have that many data points. We only have 6 data points. But if this was a grade 9 question, I'd say, yeah, there's a correlation here. I could draw a line of best fit. And in the lessons going forward, we're not going to be just guessing on our lines of best fit. We're actually going to find the actual equation of the line of best fit. But, if you're in grade 9, you do something like that. And maybe say there's a moderate, maybe strong, positive, moderate positive correlation, but we're not going to be guessing because we have a formula that's going to give us a value which will tell us exactly how strong this correlation is. So draw a scatter plot of the data. Does the scatter plot suggest any linear correlation between the two variables? Absolutely. So I'm going to say yes. There appears to be a moderate, maybe strong, and you could use 2 descriptive words like that. If you're really stuck between, just say moderate strong. Positive linear correlation. Alright, so now we're going to try to verify this. So we're going to fill in all our values here. So you would need a little table like this. Alright, here we go. So get my pen ready. So I'm going to take each x value and square it. So 4 squared, 8 squared, 10 squared, 9 squared, 11 squared, and 6 squared. So there you go. So you squared all the x values. Then you're going to do the same thing for the y values. So 1.6 squared will be 2.56. 2.4 squared should be 5.76. 2 squared is 4. 2.76, 4.41, 4.84. All right, and then lastly, or not lastly, but almost there, we need to multiply each x times y. So 4 times 1.6 is 6.4. 19.2, 10 times 2, 20, 23.4, 23.1, 13.2. So we almost have all the information we need for this formula. Let's see if we have it. So n is 6. And then I need the sum of all the x times the y. So I have all the x times the y's. I need the sums. So I could have wrote the word sum here if I wanted. So the sum of x would be 48. The sum of y is 12.9. The sum of the x squareds is 418. Sum of the y squareds is 28.33. And then 105.3. Alright, so now we definitely have everything we need. So we need the sum of all x, y. So that's going to be this right here. I multiplied all the x, y's together. There's the sum. So it's going to be 6 times 105.3. Then it's minus the sum of x times the sum of y. Well, here's the sum of x. Let me move this up so we don't have that watermark there. It's going to be 48 times the sum of y, which is 12.9. So that'll be your numerator. And then what do we need for our denominator? I need n, which is 6. The sum of x squared. So here's x squared, add it up. So 418 minus the sum of x, which is this. This is the sum of x, 48. Squared. Close that bracket. Open up the new bracket. It's going to be n, so it's 6, times the sum of the y squareds, which is 28.33, minus the sum of y, which is 12.9, squared. Close the bracket. So there's your denominator. So as long as you follow the rules of BEDMAS here and don't get too crazy, I definitely would not try to be too heroic in doing these calculations. I would take your time. If you need to do a step to do all these separately, but if you do it If you do the numerator, you should get 12.6. And then if you do the denominator, you should get 26.99. So make sure, don't just copy those down, make sure you can actually get those values. Personally, I would do this calculation first, do this calculation separate, multiply them, then take the square root. I've kind of gone ahead and skipped a few steps. And at the end of the day, you finally get your R value, 0.467. Now what? Well, this is what we've been after. This is going to tell us the correlation. So if we go back to our little graphic here, we have 0.467. If we see where this lies, it's approximately right here. So this is confirmed as a moderate positive linear correlation. So he can conclude that there is a moderate positive linear correlation. Now, it's very important to make this distinction. Does that mean that the temperature is causing the yield to go up? Just because two variables are correlated does not mean that the one variable is actually causing the other variable to move. Correlation does not equal causation. Eventually, we want to try to prove causation. Prove that the one variable is causing the other variable to move. So just showing that two variables are correlated is a good start, but it does not prove that the one variable is causing the other one to change. So I'll just write that in here. Does not prove that the temperature is causing the changes in yield. So causation does not, or correlation does not equal causation. Correlation does not equal causation. And there you have it. So the last page of this is just using Fathom and technology. If you have this technology or you want to take the initiative to download Fathom and learn how to do this, by all means, but obviously we won't be doing that given the current situation. So this part is obviously optional. I will post the suggested homework at the bottom here. And that does it for this lesson. So again, if there's any questions or concerns, just please email me and I'll do my best to help you as best I can. Take care.